Hello and welcome back to another video. This is a real-time sensor fusion dashboard that I built with Rust, React, and Python. Here I am in VS Code. There's not a whole lot going on over here, but I want to talk about this a little bit. In order to fire this up, there are three terminals. Let's do it. CD backend. Okay, so CD, this is super basic, right? It just means change directory. Think of it like opening a folder on your computer, except we are doing it through the command line. The backend folder is where all of my Rust code lives, and before I can run any program, I need to be in the right folder. That's it, simple, enter. Okay, now the next thing is I'm going to type cargo run space dash dash release. Okay, before I hit enter, this is where it gets interesting. So cargo, yes. Let me explain what cargo actually is, because this is important. You know how when you're writing JavaScript, you use npm, or Python has pip? Well, Rust has cargo, and honestly, it's one of the best package managers I've ever used. It's been around since, I believe, 2014, when Rust was first getting serious traction. And it does way more than just download packages. So when I type cargo run, three things happen. Cargo checks all of my dependencies, like, hey, do I have all the libraries this code requires? It compiles my Rust code, and compilation in Rust is, well, let's just say it's intense. The compiler is incredibly strict. It immediately runs the program. But here's the thing though, and this is crucial. I did not just type cargo run a moment ago. I typed cargo run space dash dash release. This is the debug versus release. This actually matters a lot. If I had just typed cargo run without the space dash dash release flag, I'd be running in debug mode. Debug mode is great when you are developing because it compiles super quick, like 2 to 3 seconds, right? It includes all these debugging symbols, so if something crashes, you get this beautiful error message. But it runs slow, like really, really slow, man. So we are talking 10 to 100 times slower than release mode. Now, why would debug mode be that much slower? Because Rust isn't optimizing anything. It's basically saying, okay, I'm going to translate your code directly into machine instructions. Excuse me, no shortcuts, no optimizations, just a straightforward translation. This makes the debugging easier because the compiled code looks a lot like your source code, right? But when I add space dash dash release, everything changes. Everything. Now Rust is like, all right, you want this to be fast? Let's do it. Let me spend 15 to 20 seconds really thinking about how to optimize this. It uses something called LLVM. That's the low-level virtual machine, which is this incredible compiler backend that does hundreds of optimizations. Here's a concrete example for my project. In debug mode, my sensor processing runs at maybe 5 to 10 updates per second. In release mode, 50 updates per second consistently, no problem. That's a 5 to 10 times performance difference. And for my project, this is critical because we are processing sensor data at 50 hertz. That's 50 times every second. So I need every millisecond of performance I can get. So what's actually running when terminal 1 is active? All right, so once this Rust program starts, what is it actually doing? Let me break it down a little bit. The sensor simulation engine, I'm talking a lot, and that's the purpose of this video. So if you don't want to hear it, skip ahead. The program is simulating two sensors running at completely different speeds. An IMU, that's the inertial measurement unit, the accelerometer and gyroscope running at 50 hertz, a GPS running at 1 hertz. Now you might be thinking, why the different speeds? Well, this is exactly how real sensors work. IMU, or the initial inertial measurement unit, chips can update hundreds or even thousands of times per second because they are measuring physical forces directly. There's no complex processing required. But GPS has to receive signals from satellites that are 20,000 kilometers above Earth-ish. Decode those signals and calculate your position using timing differences measured in nanoseconds. That takes time. Most consumer GPS chips update once per second, maybe up to 10 times per second if you're using a really nice one. The sensor fusion algorithm. So this is where it gets really cool. The program is running something called a complementary filter with an alpha value of 0.98. Let me explain what that means. Sensor fusion is the art of combining multiple noisy sensors to get one clean answer. It's like, imagine you have two friends giving you directions. One friend has a great sense of direction, short term, but gets lost over time. The other friend is terrible at moment to moment directions, but always knows generally where north is. That's exactly what we have. The gyroscope is great short term. It's super precise about rotation rates, but it drifts over time. The accelerometer that you're about to see is noisy as hell. It jumps around a lot, but it always knows where down is because of gravity. Excuse me, the complementary filter says, okay, I'm going to trust the gyroscope 98% and accelerometer 2%. That 0.98 alpha value, that's the trust factor. 98% gyroscope and 2% accelerometer. So why 98.2 and not 50-50? It's because the gyroscope is way more reliable for short-term measurement. We only use the accelerometer to prevent drift. It's like a gentle correction. Hey, gyro, I know you think we have rotated 180 degrees over the last 10 seconds, but gravity says we are still mostly upright, so let me nudge you back a little bit. And then the WebSocket server. Well, I'll get into this here in a moment, but I made this to talk a bit. The third thing happening is the WebSocket server. Now, you've probably used HTTP before. That's how websites work. You request a page, the server sends it, connection closes, done. WebSocket is different though. It's a persistent two-way connection. Think of it like a phone call versus leaving a voicemail. With HTTP, you are leaving voicemails back and forth. With WebSocket, you are on a phone call. Both sides can talk whenever the hell they want. Our Rust server sits on port 8080. That's just a number that identifies the specific service on the computer, and it does this. Excuse me. It accepts connections from the Python ML service. It accepts connections from the web browser, broadcasts sensor data to everyone 50 times per second. It listens for commands coming back like inject a fault, and I'll show that here momentarily. The command processor. The fourth thing, this is really cool. The backend is constantly listening for commands. When you click one of those fault injections you are about to see in the web interface, it sends a JSON message through the WebSocket telling it'll look like something like it'll say type and command, it'll say type command, action, injection fault, and then parameters, it'll be like whether we hit the Excel spike or gyro spike. You'll see. I'll show it. I'll show it here soon. So now what I want to do is let's just go ahead and get into this. Okay, so now you can see at the bottom, I do have some warnings, but I have 0 errors. The important thing is that down here, it's running, it's connected. Let's fire up terminal 2. Okay, let's go. CD. So remember, change directory, ML service. Before I continue on with this terminal, I want to talk a little bit about the real-time predictions. So in the real-time predictions, every time a new sensor reading comes in, roughly 50 times, well, 50 times per second, we extract the 14 features, it runs it through the isolation forest, it calculates the anomaly score, send the score back to the Rust backend via the WebSocket. The Rust backend merges this score into this broadcast. I'm trying to think if there's anything I really wanted to cover because this is kind of this isn't for a class or anything, but I'm purposely talking a lot because I learn more when I kind of try to teach it, but I don't want to talk forever in a day, and I feel like I've already talked quite a bit. I'm just looking at my notes to see if there's anything I really want to talk about. No, I mean there is and there's not. Okay, so I'm gonna go ahead and get into this. I'm gonna do Python dash x etf8 src /main. I'm gonna explain what this means here later. All right, here goes all the. Okay, it's taking a moment here. There we go. Takes it a moment. Look at that. Now that's what this terminal is going to do. Anomaly detected, anomaly detected. I wish I could slow that down for you and show you, but I can't. Now here is terminal number 3. I need to change directory now into the front end. And this is going to be the npm run dev. Okay, so now this is going to fire up on another. Oh, I need to follow it first. Okay, now this is going to fire up on one of my other monitors here. Let me pull this over. All right, check it out. Now I have this anomaly message at the top. It'll pop up every once in a while, just letting me know, hey, an anomaly detected, whatever. But this is the sensor fusion control dashboard, and I'm going to talk about this while this thing's doing what it does. Yep, anomaly detected. Now I can click it out, or it'll just go away on its own. So there. You can see here I've got the orientation window. Here's the gyroscope. Here's the accelerometer, and here's the anomaly detection down here, which is pretty cool. Here's the fault injection window I was talking about. Here's your velocity, your GPS telemetry, IMU telemetry, and here's your system health. And right here it says I am connected. Okay. Now if I can, let's see. I can change a gyro spike. You won't really see too much of the, let me close this. You won't see too much of that. It's rather subtle when I hit gyro spike or accelerometer spike. But it is there. Where you really start to see it happen is if I do high noise. See that there? And up here, you see the difference there? Now let's talk about this. I'm going to zoom in on this so you can see this a bit better. Okay, let me scroll down here. All right, so this is my drone. I can actually hold and move it around. It's moving, and you can see the fan blades. There's a different axis. There are the axis points. Now, it's not 100% perfect, but you get the idea. And I can zoom out. I can zoom in really close to the drone. And there it is, moving along. Thanks to Three.js. Let me zoom out of here, or just hit 0 to reset. Now I can zoom in and out of the orientation visualization here. Oh, there's an anomaly message. Let me click on that really quick. And then I can move it around like that as well if I want to. Okay, so I'm going to talk about this a little bit. If you want to listen. If not, then I get it. Okay, so let me see. So terminal. What was I talking about last? I'm trying to remember what I was talking about last. I talked about the release. Okay, so yeah. That's right. I said I was going to talk about this later. I was in Terminal 2. Okay, so when I CD'd or when I changed directory to the Python machine learning service folder, then I typed, what did I type? I typed Python space dash uppercase X space UTF-8 space src / main.py. All right, what the hell does that even mean? Well, the Python invokes the Python interpreter Python 3.12 as of December 2025. The dash uppercase X space UTF-8. This is a Python 3.7 plus command line option. So what is the UTF-8? I, you know, I had wondered that for a long time, and now I know, and I'm gonna share it. So UTF-8, it's a Unicode transformation format 8-bit, a character encoding system that can represent every character from every writing system. It uses 1 to 4 bytes per character, ASCII or ASCII characters in English, 1 byte, emoji, special symbols, 2 to 4 bytes. Why do we need it? Our Python code uses emoji characters like a check mark, an X, exclamation mark, a little robot logo, stuff like that, right? For logging. Windows command prompt defaults to CP1252 Windows 1252 encoding. CP1252 cannot display emoji. It would show garbled text crap, right? And or just crash. So the dash uppercase X space UTF-8 forces Python to use UTF-8 for input and output. This ensures our emoji and Unicode characters display correctly. Technical detail, this sets both the Python UTF-8-1 environment variable and configures system out and system I can't remember, was stderr to use UTF-8 encoding. Without this Windows, you'd see Unicode encode error. Unicode encode error. Geez, say that 10 times fast. Or say Unicode encode error char map. Codec can't encode character or something like that. So and then the src / main.py. This is just the entry point for the ML service. That's all. So you saw all that scrolling. You saw that crazy scrolling in Terminal 2. So what is Terminal 2 actually doing? Well, the Python ML service performs real-time anomaly detection. That's why it was constantly scrolling. And it's not, let me move this over here really quick. If I go to Terminal 2, it's just hauling ass and it's not gonna stop. Okay, it's not gonna stop. And another thing I wanted to show is, so I have the project open up on another monitor. If you look at the very bottom here, if I hit Excel Spike, received command Excel Spike, injecting accelerometer spike. If I do gyro spike, received command gyro spike, injecting gyroscope spike. If I hit reset all, received command reset, resetting all faults. Now let me pull this back over here. Or actually, let me go back to that one because that just keeps moving forward. I want to put it back on this terminal because I'm still talking about that terminal. See how everything kind of mellowed out now? Let's do a high noise. You see it starts picking up again. All right, so back to term anomaly detected. So WebSocket client, this is terminal 2. So it connects to the Rust backend. It receives 50 sensor data packets per second, maintains very persistent connection with auto reconnect. The feature extraction you have, what do you have? Accelerometer, you have XYZ, gyroscope XYZ. I can never say this correctly. The Euler angles, roll, pitch, yaw, right? Velocity, magnitude, GPS speed and heading, confidence and system health, which is over here. You have the isolation forest algorithm. So what is it? An unsupervised machine learning algorithm invented back in like 2008. Um, I can't think of the guy's name. I don't know. So how it works, it builds 100 random decision trees. Anomalies are isolated with fewer splits. They are easier to separate. Normal data requires more splits. It's denser. Outputs an anomaly score from 0.0 normal to 1.0 definitely anomalous. And adaptive learning. It maintains a rolling buffer of about 50 samples. It retains the model every 100 samples, adapts to changing sensor patterns, combines ML score of 70% with statistical Z-score 30% for robustness, and real-time predictions. You've got processes each data point in less than 5 milliseconds. It calculates anomaly score, sends score back to Rust backend via the WebSocket. The backend merges score into the broadcast stream. So there's a lot going on here. I mean, it's not a whole lot. I got this. The reason I built this is because it's actually funny why I built this. I built this project because not that long ago, I was watching the movie Flight of the Navigator again, and NASA is shown in that movie, and I was thinking, I'm always thinking of different projects I can build, different challenges I can tackle. And I thought, it'd be kind of cool to build something with NASA in mind. I mean, I've never seen a NASA facility. I don't know anything about it, right? I just was thinking, what can I do to a dashboard that's got multiple terminals, that has all this, junk going on. And anyways, long story short, I was watching Flight of the Navigator, and it inspired me to make this sensor fusion control panel. And think of this as more or less a demo, right? There's a lot I could expand on this, but that's pretty much it. There's a lot more I could talk about it. I could think of like real world applications. Again, Flight of the Navigator makes me think of NASA or the aerospace industry, commercial aircraft, flight control systems, maybe like a anomaly detection system to help prevent catastrophic failures or something. I don't know. And then I started thinking about drones and robotics, spacecraft, stuff like that. So yeah, that's why I built this, and that's all I want to talk about. So I hope you enjoyed it, and I will see you in the next one. Take care. Bye.